Hi, everybody. So I just want to go over a few things about acids or bases, and then you'll continue to add in some details as you go through the Nearpod. All right, so just a few reminders. When we talk about something as an aqueous solution, we're basically talking about anything in which water is the solvent. So for our purposes in biology, that's mostly what we're talking about. How is the pH changing in this aqueous solution? What are we adding to it that's making it more acidic or more basic? When you get to chemistry, you'll talk about some other types of solutions that can be acid or basic. All right, so for us, we're going to focus on water. And if you had a solution of just pure water, most of the molecules are present as H2O, right? Those covalent bonds are strong. They don't really pull apart, but a small amount of it does. And it forms H3O plus, which is known as the hydronium ion, and OH negative, which is a hydroxide ion. All right, and in a solution of just pure water, the hydronium equals the hydroxide, and that means that water by itself is going to be neutral. Okay, so what happens though as we increase the hydronium or increase the hydroxide? That's when you get solutions that are acidic or basic. One little note here, I drew this out as the hydronium ion. Biologists, for the most part, we use this interchangeably with just saying that the hydrogen ion concentration increases or the proton concentration increases. So mostly I'll just talk about hydrogen concentration, but you'll notice on the little simulation you do that it'll mention hydronium ions. You'll cover this more in chemistry, so don't worry about it now. Okay, so when we have more, a solution that produces hydrogen ions, so that there's more hydrogen ions in solution, then you wind up with a solution that is an acid. So here's an example, HCl, hydrochloric acid, is a strong acid. And so in water, this completely separates. And you can see here, it's producing hydrogen ions in water. And that's going to then make the water more acidic. Bases are compounds that produce hydroxide ions when dissolved in water. So an example here would be sodium hydroxide. So when this dissociates in water, it releases hydroxide ions and makes the solution more basic, or we can say more alkaline. Okay, so now let's relate how acidic a solution is, or how much hydrogen ions are in solution, to the pH scale. So the pH scale is a common way to discuss how acid a solution is or how basic a solution. So if we look at this picture over on the left, you can see that we're starting with the most acidic down at the bottom, and it's going up to the most basic up at the top. All right, so here's water. This is our neutral solution. So pH 7 is considered neutral pH. All right, as we go lower than pH 7, we're becoming more acidic. And as we go higher than pH 7, we're becoming more basic. Okay, and remember, alkaline is another word for basic. Now let's look and see, all right, how does this relate to the hydrogen ion concentration? So let's look over on the right. Now, first thing you have to do is look carefully at the scale, because this one's going in the opposite direction. We're starting at the top with pH 0. Here's pH 7 in the middle, and then we're ending with pH 14 at the bottom. So we're starting out with very acidic and going to very basic. Okay, so that should look kind of the same if you just reverse the two. But notice here, it's also giving you not only the pH, but the concentration of hydrogen ions compared to distilled water. So this isn't the overall concentration. You'll see that in the simulation you're going to do, but this is just comparing it to pH 7. So pH 7 would be considered 1, because that's what we're comparing it to. And as we go more acidic, Notice what's happening to the hydrogen ion concentration. We have 10 times as many hydrogen ions as water, 100 times, 1,000 times, 10,000 times, etc. So every time we go up 1 pH unit, we're going up times 10 in the hydrogen ion concentration. All right, and if we start at pH 7 and we go more basic, now look, we're going to continue going down. So notice pH 5 is 100 times, 6 is 10, pH of 7 is 1. Now pH of 8 is 1/10, 9 is 1/100th, 10 is 1,000th. So again, we're now going decreasing by multiples of 10. So that's a log scale when you see that going up and down by orders of 10. And the exact relationship is that the pH is potential of hydrogen, is the negative log of the hydrogen ion concentration, or the negative log of the hydronium concentration. Either or. All right, so I'll tend to use this. I think the FET you're going to do in a little bit uses this, but it's referring to basically the same thing because this hydronium ion is going to release hydrogens. Okay, hope that gets you set up, and continue on with your new pod.